Okay, so in the last video we said that hydrogen, or protons rather, are the most polarizing cation possible. So what happens is that, again, if you have some sort of electronegative atom, so oxygen in this case, we end up with this delta plus, delta minus, and then so we get this dipole moment. And I figured out the dipole moment arrow goes towards where the electron goes. So that's my dipole moment arrow. So we form a dipole. And then, so basically, typically electronegative atoms, so if you have some sort of, let's say, fluorine, of course, is even more electronegative. We have oxygen, nitrogen, chlorine. These all pull electron density away because they're very electronegative. And so these can all form these dipole moments. And then as a result, then we can get hydrogen bonding. So actually, let me just kind of quickly put so requirements for hydrogen bonding, for H bonding. So we need a big delta chi. So again, these are the very electronegative atoms. So the delta chi between hydrogen and these atoms is big. And so again, that gives us the dipole moment. And then the other part of what we need for hydrogen bonding is we need this X atom to have lone pairs. And that's how we can interact them with the kind of positive partial charge on hydrogen. OK, and so the classic example that we all experience every day is hydrogen bonding within water. So here's a water molecule. We still have our partial charges, delta minus, delta plus, delta plus. So overall, we have a dipole moment pointing upwards. Right, it should be down this bond, but then we have two of them, so they cancel each other out. And then so I guess the key point here is that the H polarizes the lone pairs. And then so we can then form, the word I have written down in my notes is semi-covalent, but we won't just, we'll just say kind of, they're called non-covalent interactions. Intermolecular. So by non-covalent, I mean you're not doing the typical covalent bond where you have one electron from each atom and then they interact together. It's actually, in a way, it's almost like a dative bond here. So here we have our partial charges, and then if we have a second molecule of water coming in, here's my second molecule of water. So we have, of course, lone pairs. And then so we have our delta minus, delta plus, delta plus. We can then form an interaction between this lone pair and this hydrogen. And then we form, those interactions continue on further and further. We could draw another molecule of water here, et cetera, et cetera. So it keeps on going. So the polarized hydrogen can interact with another electronegative atom that has lone pairs, and that goes on and on. So of course, the effect of here is that the boiling point of water is 100 degrees. If we go down in that same group, group 6, sulfur is right below it. So hydrogen sulfide, H2S, the analog of water, is a gas at room temperature. So it experiences some hydrogen bonding, but of course our delta chi is smaller between hydrogen and sulfur, so hydrogen sulfide has less hydrogen bonding. We'll kind of go over some data in class for this. And let's say the most extreme example, we said fluorine is the most electronegative atom. So if we have HF, here's HF, right? We have a big kind of delta plus, delta minus going on because of the electronegativity difference. If we have a fluoride anion, right, we should experience very strong hydrogen bonding between this delta plus and this minus charge here. And in fact, we do. And then so we can actually isolate a salt of FH F minus. This is a stable anion, kind of like this kind of pair together. And so we can actually get like the potassium salts of that, and you can isolate that and you can use it. So this is an example of such strong hydrogen bonding that you actually, you can even consider this a 3-center 4-electron bond rather than just like a pure weak non-covalent interaction. Typically, we think of non-covalent interactions like hydrogen bonding or the halogen bonding we did in problem set 1 as weak and not very good compared to a real covalent bond. But in this case, it's so strong that you can't distinguish the two. It's not an asymmetric molecule. It's now a symmetric, fully electron share delocalized species.